the potential energy function. This is one of the most important ideas in all of physics. This is huge. So hopefully I do a good job of trying to get you to understand this. So physically, we've already defined a potential energy function because of that minus sign. So physically, we've already have defined the potential energy function. And what I mean by that is that if you look at my system, whether I had, in our previous case, we talked about a hand and this guy was doing work. Now what we're doing here is that we're saying that that work does what? It changes the energy. And we said that this changes the potential energy of the system. And if I only focused on internal forces, what we said here is that when I look at this system here, I'm seeing this here, that if I looked at the work of my hand, that work of my hand, this guy was what? External. If I looked at the spring, this guy was internal. So if I only looked at internal workings that are going on, it's the work of the spring that really changed the potential energy of the spring. So work and potential energy are two sides of the same coin. One side is the work of the spring, the other side is the stored potential energy. So then I look at this way here. So then we said that there's a negative work done by a conservative force. And the key word here is that negative term right here. That's the key word. And what we found here is that this was the work stored as potential energy. That's what the work energy theorem tells us here. So then let's write this out mathematically. So from the work energy theorem, what do I see? Well, I see that I have work. That work, as I go from one location to another, is about the conservative force. And I'm integrating it over this thing. What we get here is that, look at the minus sign. I'm going to move that minus sign to the potential energy side. So it's customary to put the minus sign with the potential energy, not with the work. So all of a sudden, I have a new function in terms of position here. Okay? So I could either write it this way, or I can write the potential energy function would be minus the work or I could leave this as a derivative where I say here that the derivative of this function, this potential energy function, will then be minus the force. So that's what our picture shows, and that's what it is right here. So let's go look at this thing here. Let's go look at the details. That's our definition of potential energy. So I need to make some remarks, and then we want to start looking at things. So here we go. I'm going to start off by making a series of remarks. So the first thing that we say, works implies a displacement change. So anytime we start talking about working implies a displacement change. We've already had this discussion before, but it's got to be done. And then I'm going to ask you a simple question again, which I've asked you again several times. Can one talk about doing work only at one point? Can you have work if you only talk about one point? The answer is no. This is meaningless. It has no meaning. So when we talk about energy implies changes in energy, right? It only implies changes in energy. So when we say this is meaningful. One cannot define potential energy at one location. This, as you could possibly already know what I'm going to say, is meaningless. Don't talk about energy at one point. By the way, textbooks do it all the time. Online, they say it all the time. Even I will say it. But you got to remember, that is a meaningless statement. Okay? So you cannot talk about energy at one point. So 2. If a force is not conservative, then a potential energy function cannot be defined. As an example here, consider frictional work. So if I take a block, let me draw a surface first. You could imagine that it does something like this. And so what we want to do here is that we want a top view. So you could imagine that I take a block, right? And here's my block right here. And what we're going to do with this block is that we're going to push it across this surface here. And then it's going to get all the way over to here. And so when we look at the distance that this block traveled, we can see here that this distance is this distance right here. But now, what happens if the block takes a crazy path? Right? I start off with my block like this here, and it's going like this, but now it goes like this, goes like that, and then it finally ends it right here, where what it does here is that the distance, the distance to travel from, let's say, A to B, let's call this A, this B, this A, and that B. Well, here, as you're looking at this path, you're seeing that this path over here is much longer, right? This is a much longer path. This is a shorter path. So what you're going to find here is that when I go and I calculate the work of friction, because this is a constant force, this is going to be the work of friction times D. But this guy over here, because it has a much longer path, that covered more work. Work did of this friction is a lot more. So therefore, these two are not the same. And that's because friction is path dependent. And if it's path dependent, that means no potential energy, no potential function can be defined. That's what I mean by this here. They have different amounts of workings that go on. So, last thing here. In this course, we will only consider two conservative forces. And that is the spring and gravitational forces. So because of that, that means that I can define a spring potential. Because of this, I can define a gravitational potential. And the way we typically write these here is we write that with an S and we write this with the G. So, but there are other conservative forces. What you'll find here is that, like the electric force is conservative. If you go inside the nucleus, it turns out that there are forces called QCD forces. That's a conservative force. There are other forces that we can look at that are conservative. But in this course, we only have two. So now I come to the last point before we start talking about using all of this stuff. And this last point is an important point. And if you can get a good picture of this thing, if you go in to calculate, go in to take 4B, like next semester, you're going to see here that this picture becomes super, super important because in 4B, the electrical potential energies are very, very abstract. And so it really helps to have a picture to go along with this thing here. So here we go. The last thing I got to talk about before we get in deep into the examples here is that we want to talk about the reference potential energies. Okay, so what you're going to find here is that what's important with this thing here is that since since only changes in potential energy are meaningful, there is a reference potential that is arbitrary. And in fact, this arbitrariness actually makes calculations easier. It's like you have this constant in your pocket that you could walk around with and apply it to make your calculations easier. So let's go check this out here. So what I can do here is that I could talk about the spring potential, but I think it's going to be easier to talk about the gravitational potential because it's easier to visualize what is going on. So here I go. So the first thing I want to do here is I want to look at the gravitational potential. So the gravitational potential energy, you'll see that if I'm writing it, and if I have to, I try not to write the whole word, and this guy is really the thing that we want to look at. And in this case, this guy depends on y. So check this out. This is the notation that you're going to see me use a fair amount of time. If we know that we're dealing with just only gravitational potential, I'll just write PE. If you know that I'm only talking about spring potential, I'll talk about PE. But if I have to mix them, then I will differentiate them. So here's what we know. So the first thing that I want to do here is that I want to derive the potential energy function here. So let's go and derive the potential energy function. And when we look at this thing here, we say that we have a potential energy function. Like I write the G, and this guy's going to be negative, and then I'm going to have a height change from y initial to y of f of g dy. So if I compute this, I'm going to get minus, there's my minus sign as we expected, then I'm going to get mgy minus mgy naught. And this, by definition, really represents what we call the potential, because this comes up so many times, we go in and we define a potential energy where U of G is equal to mgy. And this is what we call, of course, the gravitational potential energy term. Again, single point, meaningless. But here's the thing that becomes important here. This term right here is known as the reference potential. Okay? And that's what our discussion is about. This is our reference potential. So what I want to do here is that I want to draw two pictures. There's the force picture, and then there's the energy picture. Okay? So here's our force picture. And when we're thinking about this, is that we're going to drop a ball. So let's set up a ball that we're going to drop. So you could imagine that we have a table. Okay. And we could imagine that this table here is this, you had a bunch of lime green paint at home and you decided to paint your table this icky green color. Well, I don't know, you may really like that, I'm sorry if you're in that position, but that's besides the point. And so what we're going to do here is that we're going to imagine that we're going to drop the ball. Okay. So what we're going to do here is that we know that this is the floor, and we're going to imagine that we're going to take a ball and we're going to drop it right here. So I'm going to drop a ball from this height. And what we're going to do here is that we're going to drop it in such a way, you know what? I think I'm going to change how I'm going to drop it. I'm going to move this over here. And I imagine that I'm going to drop 2 balls. In each situation here, I'm going to say that I'm going to drop a ball onto the table. And what you're seeing here is that, of course, as the ball drops, in each of these situations, I'm dropping it onto the table. It's going to look like something like this here. Right? So I'm going to call this ball case number 1, and I'm going to call this ball case number 2. So when I look at this picture here, I want the energy picture. So what does the energy picture do that's different than this? So the first thing you want to pay attention to is look at the potential energy function. Okay? Look at the potential energy function. Now, if I go and I plot the potential energy function of this system, I'm plotting the gravitational potential. But what is this equal to? mgy. So I'm going to do this y. So why does the ball fall? Well, the ball falls, of course, in each case because what? We have the force of gravity acting on this. So this tells me that if I have the force of gravity, I can see that there's going to be a height change as this ball falls from, positions 1 and 2 all the way down. But what does the potential energy function look like? According to our picture here, I'm going to say that this potential energy function is a ramp. Right? This is the potential energy ramp. And you could see why, because it's a linear function of y. And that's what it does here. So when I look at the floor here is y equal to 0. I'm going to call that y naught. And then here, we could say here is that y naught here is going to be equal to 0. So now let's look at this thing. So the only thing that matters is potential changes in potential energy. Okay, so let's say this again because I have to beat this into you. So the only thing that matters is changes in potential energy. So let's look at this thing. So what I'm going to do here is that I'm going to set my reference potential to 0 at the tabletop. So what I'm going to do here is that now I'm going to list numbers here. So I set y initial equal to 0 here. But now I'm saying I'm going to put y prime initial equal to 0 at the tabletop. So what I'm saying here is that where y initial prime is equal to 0, which is at the tabletop, that tells us here is that the potential energy function, y naught, which is known as the reference potential, that tells me that this is going to be mg y initial prime, that is 0. So let's say that we drop the ball 2 meters above the table. You know what? I should be a little bit more careful because I think I'm going to get funky with my numbers here. So I'm going to go back and change what I just said. And only to make it a little bit more clear. I don't want to set 0 and 0 here. What I'm going to do here is I'm going to set this to 1 meter. I apologize for that. I should have thought about this a little bit more in depth. So that means I'm going to set my location y initial prime to 1 meter. So what that means here is that if I do that, this is my prime, I'm going to set that guy to 0 here. So my reference potential at y initial prime is going to be 0. So if I do that, then that means that we now view the world from the tabletop. So relative to the tabletop, there is no ground. So what this tells us here is that if this is my tabletop right here, this guy is how I view the world. And when I look at the ball's up here, and the ball's going to fall down to here. So when I look at this thing here, what you're seeing here is that here's where the ball starts, and then here's where the ball's going to end. And what you're going to see here is that I'm going to say that the height change from here to here is then going to be 2 meters. So when I look at the potential change here, what do I see? Well, if I view this from this world here, what you're seeing here is that the ball drop, so then the ball drop relative to tabletop looks like this. It says that, okay, so my change in potential energy of gravity is going to then be my change of potential energy relative to the 2 meter mark minus my reference potential. But wait a minute, my reference potential tells me that at y initial prime equal to 1 meter, that potential is 0. So then I come in and I say, what's my change in potential? Well, it's going to be mg times y minus 0. So then this will be this mg times this 2 meter value equal to 0. That's my change in potential here. But I don't have to view that world in this way. What I can do here is that I can also set my reference to be 0 at the floor. So now, in other words, what this tells me here is that if I set y equal to 0, the only thing here that my reference potential at y of 0, this is where I'm going to define my potential energy to be 0. So what this tells us here is that we now view the world from the floor. So then I come back and I redraw my picture, and it goes like this here. I have my table. And now that I have my table, now the only thing I know is that my little guy here is standing at the floor at y equal to 0. But where is the ball? Well, we know that the tabletop is actually at 1 meter, and we know that the ball is 2 meters above that, so that means it has to be at 3 meters. So if I now look at the falling of the ball, and if it falls down, what we're seeing here is that as it falls down, what am I seeing here? Well, my reference potential is what I did here. So now if it's coming from the floor, I'm saying, what is my force of gravity change? Well, where did it start off? It started off at a potential that's at 3 meters off the ground, but where did it end? It ended at 1 meter. So when I go and I look at my things here, you could see that this guy is not 0. So if I look at this thing, I'm going to get mg times 3 meters minus mg times 1 meter. And I can see here that I'm going to get mg times 2 meters. And if I compare this answer over here to this one, you could see here is that I get the exact same result. And what that's telling you here is that the reference potential is arbitrary. So the reference potential being set to 0 is arbitrary. And so therefore, we choose this reference that best suits us. We choose it to make it the most useful.